Hey there, and welcome. So, you've got this pile of dense lecture notes on network security, you're staring at them, and you're feeling a bit lost? Don't worry, you are in exactly the right place. Today, we're going to demystify one of the most important protocols on the entire internet, TLS 1.3. This is the magic that keeps your online life private and safe. Let's break it down together.
You know that little padlock icon in your browser's address bar? You see it all the time, right? It's supposed to make us feel safe, but what is actually going on behind the scenes to make that lock show up? Well, that's what we're going to dig into. We are turning those confusing notes into something that just clicks.
So, here's the game plan for today. We're going to start with the absolute basics. What is TLS? Then we'll get into the super important handshake that kicks off every secure connection. After that, we'll look at the different protocols that work as a team, and we'll do a deep dive into the record protocol. That's the real heavy lifter here. We'll see how data gets checked on the other end, and finally, we'll wrap up with the key takeaways you absolutely need to remember.
All right, let's dive right in. First up, what in the world is TLS 1.3? Well, you can think of it as the gold standard for keeping our internet connections secure.
Think of it this way. Your computer is the client, and the website you're visiting is the server. Basically, TLS, which stands for Transport Layer Security, builds this private encrypted tunnel between the two of you. Anything you send through that tunnel is completely scrambled, so it's just gibberish to anyone trying to snoop. That's the main goal right there.
Okay, so how does this magic tunnel even get created? It all kicks off with something called the secure handshake. Before you send any of your actual data, like your password or credit card info, your browser and the server have to sort of introduce themselves and agree on a secret code for their conversation.
And this whole process, it's kind of like a secret dance, really. First, your browser, the client, sends out a hello, but it's not just a simple greeting. As you can see in step 1, it's sending an offer with all its security tricks plus a random number. Then, in step 2, the server throws in its own random number, and they mix them together to cook up the secret keys for this one session. But wait, how do you know you can trust the server? That's step 3. It shows its ID, which is a digital passport called an X.509 certificate. Your browser checks it to make sure it's legit. And sometimes, though, it's less common, the server might ask to see your ID too.
Now here's where it gets really interesting. See, the thing is, TLS isn't just one big thing. It's more like a team of specialists, a whole family of protocols that have to work together perfectly. Each one has a very specific job to do to keep things secure.
And on this team, you've got 3 main players. You've got the handshake protocol, who's the diplomat. You've got the alert protocol, the team messenger. And then you have the record protocol. And this is the one we're really going to focus on. It's the absolute workhorse. Every single one is crucial. Okay, so first you've got the handshake protocol. This is your diplomat. Its whole job is to negotiate the security rules. It agrees on stuff called cipher suites, which are really just fancy recipes for encryption that both sides agree to use. It also creates those secret keys, and of course handles the ID check to make sure everyone is who they say they are.
Then there's the alert protocol. Think of this one as the team's emergency messenger. If anything, and I mean anything, goes wrong, like maybe the server's ID is expired or it just looks fishy, this protocol is the one that sends up a red flag. It might just be a warning, or it could be a shut-it-all-down fatal error that ends the connection right then and there.
And that brings us to the real star of the show today, the record protocol. This thing is the absolute workhorse of the whole operation. Once the handshake is done and the rules are set, the record protocol steps in. It takes your actual data, your email, your cat video, whatever, and does the really critical job of scrambling it up and sealing it so it can't be messed with on its journey.
All right, so let's really get into the nitty-gritty of this record protocol. If you're studying for an exam, you're going to want to lean in a little closer for this part, because this is where we get into exactly how your data is bundled up and protected as it flies across the web.
The very first thing the record protocol does is something called fragmentation. Now check out this diagram. It shows this perfectly. If you've got a big piece of data, let's say 20 kilobytes, TLS doesn't just try to shove it all through the tunnel at once. See how that big block on top gets split into 2 smaller records? It's a lot like taking a huge order and splitting it into smaller, more manageable boxes before you ship it.
Okay, but how do we protect these little boxes of data? Well, TLS 1.3 uses this incredibly powerful technique called AED. This is a super important term, so you're going to want to remember it. AED. It stands for Authenticated Encryption with Associated Data. Think of it as a 2-for-1 security deal.
The encryption part gives you confidentiality. It keeps your data secret. And the authenticated part gives you integrity. It makes sure nobody has messed with your data. So it's like a lockbox with a special seal that shows if it's been tampered with.
And here we go. This is basically the blueprint for every single one of those secure packages. This is what a single TLS record looks like on the inside. It might look a little intimidating, but trust me, every piece has a simple, logical job. Let's pull it apart and see what's inside.
So let's just walk through this. First up, you've got the content type. That's just a little label saying what's inside. Is it your data, an alert, what? Then there's the version, which is kind of funny. It's often set to an older version just to make sure it doesn't break things that aren't fully updated. Next is the length, and this is really important. It tells the receiver exactly how big the main package of data is. The payload is the good stuff, your actual data all encrypted. And then the big one, the MAC, or Message Authentication Code. This is that digital tamper-proof seal we were talking about. It's a unique signature that proves the data came from the right person and that not a single bit has been changed.
Okay, so we've packed up our data and sent it off. But what about when it arrives? You can't just assume everything's okay, right? The receiving end has to be super careful and go through this whole verification process to make sure it's safe to open the package.
So here's what the receiver does step by step. First, it looks at the length field to see how big the package is supposed to be. Second, it starts collecting all the little data packets until it has the whole record assembled. Third, it uses that secret key they agreed on way back in the handshake to decrypt the payload and turn it from gibberish back into real data. And finally, and this is the moment of truth, it calculates its own MAC on the data it just decrypted. Then it compares its result with the MAC that was sent. If they match perfectly, awesome, the data is authentic and untouched. If they don't match, that package gets thrown in the trash immediately. No chances taken.
Whoa, okay, that was a lot, I know, so let's boil this all down. We've gone through the whole process, but what are the key things you absolutely have to know, maybe for an exam, or just to really get it?
Let's just focus on the absolute essentials. So if you remember nothing else from this whole explainer, remember this stuff.
Here are your big 4 takeaways. Write these down. Number 1, the handshake protocol is the negotiator. It sets everything up. Number 2, the record protocol is the protector. It does the dirty work of securing your data. Number 3, AEAD. It's the 2-for-1 deal that gives you both secrecy and integrity. And number 4, the MAC. That's your proof, your digital fingerprint that guarantees the data is legit. If you get those 4 points, you've got the heart of TLS down.
All right, here's a classic exam-style curveball for you, a potential problem. Remember how we said a TLS record is like a big shipment broken into smaller boxes? Well, those boxes are sent as something called TCP packets. And here's the catch. If just one of those little packets gets lost or stuck in traffic on the internet, the receiver has to stop and wait. It can't put the whole TLS record back together until that one missing piece arrives. This traffic jam is called head-of-line blocking, and it's what causes that annoying lag or latency. Understanding this little detail really shows you get how the pieces fit together.
So when you step back, it's pretty amazing, right? TLS 1.3 creates this incredibly secure tunnel for our data while it's flying across the internet. But it also leads to a much bigger question. If our data is safe in transit, what's the next big challenge for our privacy? That's when you start thinking about things like protecting data when it's just sitting on a server, or privacy inside the apps we use every day. It's a great question to chew on. Thanks for sticking with me through this deep dive.